and hopefully that works. Okay, so welcome back to everyone. I think we'll dive right in now, and as soon as I can find the right thing to share, you know what? I'll go with my whole screen again, and hopefully, I've got do not disturb on, so hopefully. Um, no one texts me with anything embarrassing. That normally happens, right? So, all right. So, I think today we'll eventually get more into kind of a high level overview of the actual implementations of um, autonomous vehicles. But I wanted to start with chat about the projects a little bit more, and then we'll do a quick review. Try to do that each week. I actually posted a quiz, and I think I put that in a forum, and so that's not graded. It's up to you to do it, but obviously, we don't learn very effectively just by listening to some lecture, right? I can drone on and on and on and think I'm giving you all this wonderful information, but yeah, you're not going to be able to internalize it until you've worked with it a little bit. So that's the point of the assignments. It's the point of the quizzes. So take the quiz, and they'll be super short each week, just kind of helping you make sure that you're bringing all this information in and making sense of it. So the project wanted to kind of brainstorm some more ideas on what you might want to do on this. Again, the course is multidisciplinary, right? So it's involves a lot of different aspects of engineering and computer science, computer engineering, electrical engineering, computer science. There's aspects of all of that in there. I hope that you're interested in all of it, but I expect that you will have particular interest in particular aspects of this, right? And so that's why I'm giving you a lot of latitude in choosing the research report topic that you dive into, and also the project. So hopefully you're somewhat comfortable in working with machine learning. Maybe you've never done it before, but at least you're interested in it, right? Because autonomy does revolve a lot around machine learning. But at the same time, it's not the only thing involved in autonomous vehicles, right? So there's the aspects of mechatronics. We're not going to go real deep into that. I'll talk about that a little bit today, but not. I'm not going to write any equations down or anything like that. But if that's an area that's a particular interest to you, then you may want to dive into that, right? So you might want to do a little motor control circuit or something like that. If you're more on the embedded side, you could dive into sensor fusion type of work. You could really dive into GPS, and I've worked with GPS quite a bit throughout my career, and so I could help you get focused around an open source tool that creates or synthesizes GPS signals. And you could do that and then play with the signals a little bit. I've done some software-defined radio type work and receiving those signals, that type of thing. So you could dive into that area more deeply if that's of interest to you. You could Also do one of the other international standards. Of course, China, European Union, Russia, all have big systems, and there's India and Japan, and a few others have more regional systems. So you could even toy with some of those. You could process camera video and run that through a computer vision algorithm of various sorts. And on all this software, there's tons of software out there posted online. You can download it and be working with it right away. You got to figure out what you're going to learn from that process, right? So just downloading some code and running it isn't going to teach you a whole lot. It's not going to necessarily by itself help you in your career or help you even to get a job, right? So but it can be a great starting point, right? So you can download some code. You might adapt that code. You might tweak it a little bit to a new purpose or a new feature or something like that. You could measure the performance of the code. All right. So one of the important issues in autonomous vehicles is that we don't have forever to make these decisions, right? If we see something ahead of us, we've got to decide whether that's a danger to ourselves or to that object. Let's say, we need to decide, is that a pedestrian? Are they about ready to walk into my path? And all that has to be done within milliseconds, right? So that might be kind of an aspect of your project is measuring the performance of a few different algorithms and stuff. So you can prototype all sorts of different machine learning algorithms. Of course, we're dealing a lot with computer vision, but it's not just computer vision. You could work with some radar type signals. You can work with ultrasonic signals, that type of thing. You can work on fusion algorithms. Did I mention that already? We'll look at Kalman filters, but there are things such as the extended Kalman filter. We'll look at a particle filter implementation. So you can take these and kind of go deeper with them than we will in class or with our assignments and make something of it there. You can get your hands on data sets. I will give you a few references to data sets when we get to that part of the course. And there's a number of freely available data sets out there that you can take advantage of. You can go to Kaggle and download those. It may just happen that there ends up being a relevant Kaggle contest going on. If you're not familiar with that, that's a hosting site that hosts lots of different machine learning oriented type of competitions. And some of them are for significant prizes, cash prizes. There's other sites besides Kaggle that host these things and that type of thing. So just tossing out some ideas there. Encourage you to talk to me about things, projects that you might be interested in. I have kind of a ridiculously broad set of skills. Not always necessarily that deep, but I've had my hands in a lot of different things. So hopefully I can give you some good guidance on where to go. As a reminder, I spent most of my career in industry and various startups and that type of thing. So I've got a good sense on reducing things to actual practice and also. Anyone have any questions on that at this point? Y'all are hearing me okay, I think?
Yeah, we can hear you. I do have a question, but I'm gonna email you it rather than like ask it because it's a really in-depth question more so.
That's fine. Okay. Yeah. A couple of y'all attended my office hours today. That's great. That's part of your tuition. Is I suppose some students consider their tuition just to be just give me that diploma and grade at the end of things, right? But I hope that you guys are as seniors and grad students, you're more invested in your education at this point, and so yeah, your tuition goes into more than just an assessment and diploma. It's actually even more than just lecture. Part of your tuition is access to your professor for office hours. So I have set up regular office hours from, let's see, I got to make sure I do my time conversion because remember, I'm in central time zone. So if you get something from me um, that has a time associated with it, you need to kind of double check to see whether that's still in central time zone or if the computer has converted that to your local time zone, which I assume most of y'all are Eastern time zone. And in the New York area, but so my office hours are from 5 until 6 Eastern time. But I've also created a link um, to Google's appointment management system, so you can set up an appointment with me on Monday, Tuesday, Thursday, or Friday. But be respectful and be understanding that I'm just doing this part time. I'm mostly retired and, out there enjoying life. Well, this is part of enjoying life. I do enjoy this, but I'm not necessarily checking my email every moment. So I think it's set for you need to set up an appointment at least 4 hours out. And that gives me a chance to kind of update my plans for the day. I might be out hiking or fishing or just mowing a yard or something like that, right? So um, just kind of be mindful of that, but feel free to set up that. All right, so let's kind of review real quickly what we did last week. We talked a little bit about history. We talked about the levels of autonomy a lot, right? So, or this maybe is the most tangible thing we talked about, right? And let's see, do I have that up somewhere? Yeah, so well, this is a huge standard. It's not huge as standards go. Many standards are 1,000 pages long. The 3GPP LTE standards are in dozens of different documents, each of sizable length, and never added them all up, but they're huge. So this one is not too bad, but it's the surface vehicle recommended practice, and it's really for the automated driving committee. So, um, I encourage you to kind of take a look through this and get kind of familiar with how standards are written and how you might use them and that type of thing. So then um, let's see, do I have, maybe I don't have the list of standards, but, or that, uh, yeah, there it is. Okay, so I do have it. So here we have the, uh, well, it kind of called five, but there's really six different levels if you do include level zero, but level zero is basically no automations, right? So might be old school, um, you know, um, automatic emergency braking, that type of thing, but there's no control over the system, other than maybe some braking. So we're really talking about levels 1 through 5. 5 is kind of the penultimate level. This feature can drive the vehicle under all conditions. Well, humans can't even drive vehicles under all conditions. You put a little layer of ice on the road, and no one can really drive on icy roads. So a lot of people can't drive in heavy rain or heavy snow. People should probably pull over in those cases, right? So, exactly how extreme is all conditions is, I don't know, maybe up for debate. But yeah, level 4, that thing's fully autonomous, and all the way to the fact that there may be no way for a passenger to even take control of this vehicle if there is something going wrong, right? So, but the vehicle is designed to enter a safe mode and be able to pull off out of the traffic lanes to the extent it can. Just like, yeah, if you're, I remember when I was living in New York, but still had a house in Florida, and was driving up from Florida, and was crossing the New Jersey, Pennsylvania, New Jersey line, and about a couple of miles after that, I'm in the left-hand lane, and all of a sudden my engine just dies. And I managed to coast off to the right-hand side and park the car and call a tow truck. So humans, we gotta deal with those things, right? It was a bad fuel pump, I think, but things happen, and we might blow out a tire. So humans have to be able to enter a safe mode with the vehicle, get it off to the shoulder in most cases, and so do autonomous type vehicles. But the interesting areas are like level 2 and level 3, and I think this is where most of our vehicles are right now. If you do consider some of the robo taxis driving in some experimental cities like San Francisco, then yeah, those are kind of at level 4, still at an experimental basis. But yeah, generally there's no safety drivers in those anymore. Level 2 and level 3, you've got some high level of automation, and but you in level 2, you're still really paying attention to the driving, right? You're not texting, you're not watching a video, you are paying attention. And you may need to regain control of that vehicle very, very quickly if it prompts you to, because it can't continue safely as in autonomous mode. Level 3, okay, so now you still might need to take over and drive, but the system is actually more in control, and perhaps there's less of a need for you to actively be participating in the driving, right? So those are important concepts for us to kind of remember. So do we have a question there? Let's see.
Yeah, so my question is just, so between level 4 and level 5, is the only difference really just like the conditions that the vehicle could drive in, or are there like other differences between them?
Yeah, so when we look at that table, it's really, everything is the same except, yeah, in level 4, there's more of an expectation that the system might need to enter a safe mode. Whereas in level 5, it's expected to handle all sorts of different conditions, right? And that might be traffic conditions, or environmental conditions and that type of thing. One of the kind of issues that have popped up recently in San Francisco is how these automated cars are dealing with the presence and detection of emergency vehicles. And in some cases, they are recognizing that there's a fire truck and they just stop in such a way that in a few cases they've actually blocked the fire trucks and the fire trucks can't go on their mission, whatever they're doing. And so it's been a bit controversial. So it's like clearly level 4 type behavior. It's in the case of if a human was behind that, the human hopefully would be able to respond appropriately to the presence of emergency vehicles. And so, yeah, human would be able to handle that condition, but some of these vehicles are not quite ready for that. So we could look also in some of these slides. There's a little bit more of kind of a more English language or textual type of thing. So at 4, car can provide all driving tasks and it can take care of things even if something goes wrong, right? But it might only work from point A to B, right? So you might consider that a delivery type application, right? So and if it's in some other type situation, maybe it needs more information and some more work before it can do that particular route. Full automation, this is that aspirational goal. Now you can totally ignore. In fact, there's even like images of or mock-ups of a bed in your car, right? So you can totally go to sleep while your car drives you across country. So let's see, was there another hand up or question raised there? Or
sorry, just to like elaborate a little bit. So technically, so I was like looking at like some of the level 4 stuff, and like as you said, like it was in like restricted zones. So if like those restrictions were like removed, would that be considered level 5, or it's still not like at that level?
Yeah, so that's we would really want to kind of now dive into a standard like this. And so a standard is typically also going to give you more specifics on how you actually assess these different things, right? And if we just look here, it's level 5. It's giving us some notes here and some examples, that type of thing. So regardless of the starting endpoints or intervening road traffic and weather conditions. So technically, you got to be able to handle any arbitrary starting endpoint, any kind of intersection, any kind of construction going on, whether it's rush hour traffic or not, and whether it's snowing or sleeting or tornadoing or hurricaning or whatever, right? So, and that, yeah, so typically there would be like some certification type process that would actually kind of nail all this type of thing down. So, yeah, so level 5 is still kind of very aspirational, and I would say that this is the SAE's standard, and it's basically being adopted by other entities that matter. but ultimately it's up to, like in the case of San Francisco, the city council had to approve the operation of these robo taxis, the Waymo and the Cruise robo taxis, to be operating in their cities under the conditions that they have, right? And I'm not familiar with their whole process, but I'm sure they relied on this SAE standard to a large extent. There's one interesting thing that I've seen lately is that uh, Tesla. Now we're a long ways from level 5 with the Tesla car, but the I have, for example, the autopilot version in my Model 3, and I need to keep my hands on the wheel and kind of rotate it slightly every few minutes, so that the system knows that I'm alert and paying attention. Right, and they are um, uh, extending that time interval between those prompts, so that I can maybe get away with a little bit less attention on a moment by moment basis. And so the DOT is possibly pushing back on that a little bit or asking for more information. So yes, there's a standard. Standards generally describe what is required to meet that, how to test and certify that. But then it's up to kind of like jurisdictions or agencies to decide how to apply those standards. Make sense?
Yeah, that makes sense. Thank you.
So we did a lot of talking, mostly like raising questions and having some thought experiments about legal and ethical considerations, liabilities. What about social equity and affordability of these things? We kind of talked about some of these kind of canonical type of thought experiments. These are all kind of well known and well discussed in the industry, and there's actually a lot of debate on whether these are even meaningful, right? Like this trolley type of thing where you're in action. If you don't throw that train track switch, then the trolley or train plows through a whole bunch of people, but you didn't have anything to do with it, right? So, or you throw the switch and the train takes a different track, but now that kills a single person, right? So now is it better or worse to kill many versus one? That's kind of implying that it's a better outcome to only kill one person than a bunch, but now you took an assertive action to actually do that, right? Now, so that's a thought experiment that well predates autonomous vehicles and is common in kind of philosophy and ethics type of discussions, right? But there's a debate on whether that even is applicable to autonomous vehicles, because is that really the way these things are being programmed? That there's that kind of conscious choice, and not really, as it turns out. But still, these are things that we talk about, and then all the different stakeholders, in particular how engineers might be involved in that. And then I think it's particularly relevant to talk about disruptive mindset. Is that appropriate in this field, right? So there's some sense that Tesla, and I'm not a Tesla boy. I'm gonna mention a whole bunch of times, just because I do have lots of experience with Tesla, and also because they are one of the leaders, and not the only leader, and they're debatable on whether they're actually leading others or not. But it's just one that I have a lot of experience with. And also, while I'm at it, I also have some experience with the U.S. DoD. Doesn't necessarily mean I'm taking sides or we need to take sides, and all, but autonomous vehicles are definitely being used in defense applications. So it's meaningful to talk about those things, right? So we talked about some legal issues, and which are similar to these kind of ethical issues. There's safety concerns here. What do you do when, not if, but when there's a failure in the autonomy system, right? Or sensors. What about your just maybe an inadequate training of your neural network, and it did not recognize something that it should have, or made some poor planning decisions. And as I touched on earlier, we all need to deal with tire blowouts, debris in highway. It's like when you have someone tailgating. It's one issue to tailgate and think that you have enough reaction time to stop if the person in front of you stops quickly. But kind of the more relevant thing is what happens when they suddenly change lanes because there's a whole bunch of debris in the roadway. Some ladder fell off some construction truck or something like that. And now, do you have time to either stop or change lanes without colliding another car already in that lane? Well, if you have to be able to do that, then an autonomous vehicle also needs to be able to handle that. We touched on cybersecurity, and that the safety of the system can absolutely be compromised. And then we started talking about applications. So let's move on to today's lecture, and we'll kind of dive in there and get started. So all right, so we'll look at system overview. The first part of the lecture will look at how we'll say conventional approach is. That's kind of the approach laid out in the textbook. And then we'll also look at how an alternative approach, which is kind of the Tesla approach. They don't give away all their secrets, but they do talk about their approach a lot in the public domain. So that is helpful. And as we'll see, they do take a little bit different approach. And then in the last part of the lecture, we'll hopefully have some time to talk about some considerations for different types of autonomous vehicles and different types of domains. So we'll look at the functions of an autonomous vehicle. We'll start recording some definitions. We'll obviously have lots of terms that come up throughout the course, but we'll toss a few out there right away, and then we'll talk about kind of the basic concepts of autonomy and look at that autonomous vehicle overview, and then kind of the pure computer vision or camera-based approach, and then we'll cover some use cases and challenges and all. So all right, so what are the main functions we need to implement for an unmanned autonomous vehicle? So I'm going to be a little bit redundant here on a few slides because I think it's good to look at this and kind of nail this. If we don't know really what we're trying to accomplish, we're not going to be able to accomplish it very well, right? So, and we can look at these in kind of a few different ways, right? So there's locomotion, right? Mechanisms to move the vehicle and control direction and speed over time, right? So we need that prime mover capability. Yeah, gotta be able to do that safely. When I lived in Florida, I lived next door to a professional race car driver, and so we talk about now his kids drive for him, but in racing, you're trying to get around turns as quickly as possible, considering the forces that are causing your vehicle to want to go in a straight line instead of turning. That's counteracted by the frictions of the tires and that type of thing, right? So these race car drivers get a really good feel for exactly how far they can push that. And of course, there's engineering in terms of the downforce that's presented to maximize that friction of the tires without wearing the tires out, and that type of thing, right? So, but there's a maximum of speed in which you can do things, even if there are no speed limits, right? So the autonomous vehicle has to be able to negotiate turns and that type of thing in a controlled manner. Navigation, got to determine where it is. It's that localization aspect and how it can get to a goal destination, right? So I want to get from here to the grocery store, right? That's one level. I want to get from here to New York. It's maybe another level, but not that different, right? But what about a more local type of thing, right? So is it best to stay in my current lane, or should I move to the lane to my left, or should I move to the lane to my right? As I'm, let's say, traveling down the highway, or I'm on a suburban or city surface streets, and I'm coming up to an intersection where maybe I'm turning left or turning right. When do I turn? What about those suicide lanes where you've got the middle turning lane where opposing traffic can be in that lane? And how do you determine that? So it's not just your kind of high level Google or Apple Maps type of routing, right? And then there's the payload, right? So the payload's not intrinsically part of the autonomy package, but it's the purpose of the whole thing, right? So are you a taxi service and delivering people? Are you, let's say, like my Tesla, where I kind of lean on the autonomy package to kind of ease the driving when I go long distances, or I'm in heavy traffic, or something like that, right? Or are we moving some cargo? Are we doing a food delivery, Uber Eats type of example? Or are we doing interstate semi-truck level deliveries that are autonomous trucks? Are we moving cargo around a port, a shipping port, where we have basically a whole bunch of containers coming off a container ship and going onto rail or trucks, or vice versa, right? And can that be automated? Are we carrying instruments? They might be scientific instruments, like on Mars, on a helicopter on Mars, or on the moon, or in the upper atmosphere, trying to do scientific research there. Or are we maybe doing some intelligence or surveillance, reconnaissance, ISR type of defense-oriented activities, and we might have some, let's say, infrared detectors looking for missile launches or something like that, or all the way up to weapons, right? So these payload types kind of determine how we might implement locomotion and navigation, and what aspects we need to be concerned about. If we're defense-oriented platform, we might want to stay covert as we move around. If we're carrying passengers, we have to be concerned about G-forces that are applied and how comfortable that ride is as we accelerate or decelerate or go around curves and that type of thing, right? So I think I was going to have a little discussion here, but I think I'll kind of keep going. Oh, there's someone have a comment or question there. Oh, someone, I guess, just dropped off, I think. Okay. Oh, Kevin, do you have your hand raised?
Hello.
Hello. Yeah, there we go. I can hear
I
you.
had the wrong microphone on.
I had the wrong microphone on. Okay.
So this one mainly concerns the navigation role. Goal.
Yep.
Are we trying to solve these problems completely independently, or is this also a concern about infrastructure to help these vehicles perform the test too? Like, for example, having cars communicate with each other to more effectively make navigation quicker and possible. And yeah.
Yeah. So there's as you may be familiar, there's a whole field of vehicle to vehicle communication. We'll abbreviate that as V2C. We also have V2X, where vehicles will communicate with infrastructure. So you might have radios along the highway that are reporting maybe, hey, there's some construction up ahead, or vehicles might collaborate on interpreting things that they're trying to perceive, or they might warn of, go back to the example of some debris in the roadway. As a car discovers that, it may broadcast that information and that type of thing. So, yeah, so there's a lot of opportunities there. The challenge there is that we kind of need a critical mass before those things really help us a lot, right? And that you'll see is a bit of a kind of repeating theme here in this field, and that boy, if we could just get all the humans out of the driver's seat and turn it over to the machines, then we'd actually have a simpler system. And but we're quite a long ways away from that. But yeah, it's a good point in that there's navigation of the single vehicle, and then there's how can we improve upon that by collaboration. So I actually have a couple of slides on that here in a few minutes. So all right, so yeah, the environment in which the vehicle must operate affects its design and implementation. So again, our main focus in this course is looking at passenger type vehicles driving on existing infrastructure, right? So our roads are generally striped, and in there might be some variation from region to region, but there's basic rules within the region. In the U.S., we drive on the right-hand side of the road. Slow lanes are to the right, faster lanes are to the left, and passing lanes. And a white line means one thing, a yellow line means another thing. Solid versus dashed lines, or signage, we have all that type of thing, right? But what if you're autonomous vehicle operating in a large strip mine type situation. That's kind of off-road to an extent. Take it even farther, your military vehicle. If you restrict yourself to only operating on roads, you're going to be an easier target, right? So you likely want the ability to move off-road. Let's say that's a desert type situation. Deserts can have not a lot of features, right, in which to help us to navigate and stuff. So a lot of these type of things can affect us. What if we're indoor? There's some needs to be able to navigate around subterranean type environments where you don't necessarily have nice smooth paths to move along and that type of thing, right? So what kind of navigation can you accomplish there? And of course, if you're indoors or underground, you're not likely to have a good GPS fix, so you've got to cope with that. So same type of thing if you're on the water. Now you have a whole different set of things to look out for. You've obviously got to make sure you don't run into other ships, other vessels, bridges, that type of thing. But you also need to make sure you don't run aground. And that's not so easy to do, but you can, manned vessels use charts that have depths marked on them and are, surveyed or sounded. Some charts are a couple of 100 years old and very inaccurate. And so you still have to use a lot of judgment as you're navigating. So different types of things to worry about. Now, if you're underwater, as in a submersible or submarine type of thing, then there's a whole nother set of challenges there. So is the environment known, right? As we'll see that one approach to autonomy is to, and this is the one the book talks about in detail, is to build very, very high definition maps of everywhere that vehicle might go, and down to the lane level, right? So it's more than just, again, a consumer level internet mapping app or something that's on your phone. You need to know, is that left turn lane there, is that a left turn only, or can I go straight there? Can I do a U-turn there? All sorts of different rules that we need to know if we're going to try to solve this problem with a highly detailed a priori map. But environments are still dynamic, right? Of course, we have traffic, we have road conditions that can change, construction, all that type of thing, right? So maybe there's a utility truck in the way that's servicing some power lines or something like that that's blocking traffic. So we need to design a system that accommodates all these type of things, right? So now if we get a little bit more specific, right? So some of those were kind of high level functions that we're talking about, but can we really kind of narrow this down and get very specific about how we might, specify these different functions? Well, we have a lane keeping behavior. So we need to have a system that keeps us safely in the current lane that we're in, right? Be able to follow around curves, up and down hills, deal with traffic ahead of us, possibly traffic that might merge into our lane and that type of thing, or might cross our lane. But we're basically wanting to stay within this lane. Then we have a different function, and that's when we want to change lane, right? So we might have a higher level operation going on that says, hey, it's appropriate to change lanes right now and change to the lane to our left, let's say. For whatever reason, now we need to be able to make that so, right? And how do we actually do that safely and comfortably and efficiently, right? There's ramp merging, right? So you're coming onto a highway, you're in the acceleration lane. It's very similar to lane changing, but now we need to merge within traffic. Might be two lanes merging down to one, that type of thing, right? And then there's intersection crossing, right? So now we have a high expectation of traffic crossing our path, and we want to move through that intersection and do that safely. So these are kind of the four, if you can cram a lot of different situations into one of these different specific functions. Again, assuming that there's some higher level executive going on. Think of it in terms of like on a Navy ship, or if you're a science fiction fan, like on the Starship Enterprise or something like that, right? You've got a captain or a skipper that's in charge of deciding where that ship goes. But then you have a helmsman and perhaps a throttleman that is actually controlling the rudder and the propeller or propulsion system to determine how fast to go. The captain gives orders to the helmsman, and the helmsman is expected to make that happen. So these specific functions here are kind of at that helmsman level, right? How do we actually implement these behaviors that the higher level system is asking us to accomplish? All right, let's talk about a few definitions. We're going to run into all sorts of different things, but I think these are good to get started with. Ego vehicle is kind of one of the more important ones, and that's us, right? That's the vehicle being controlled, where the autonomy package is actually running. We want to be able to refer to that vehicle specifically, because there's lots of other vehicles, right? And we need to deal with those. But the ego vehicle is the one that's actually being controlled. CIPV, that's the closest in-path vehicle. That's the one we got to worry about, right? The next closest path and vehicle might become important if things change and suddenly it becomes the closest in-path vehicle. But that closest in-path vehicle is the one that's most likely to cause us trouble, right? VRU, vulnerable road user. This can be something like a pedestrian or jogger or cyclist or anything that we need to be especially concerned about identifying. They may not be obeying the same type of traffic rules that we're operating under, right? So shadow network. So this comes up in a YouTube video that I've linked up there. The guy from Tesla is talking about it here. This is the idea that, well, you've got an operational system out there running, but Now you want to deploy an additional model out there side by side with it. So it may be consuming the same inputs as your operational model is, but it might be doing, it could be doing the same thing, but better with those inputs. So it's producing the same outputs, but perhaps in some superior way, and you're wanting to test it before you hand over control to it, right? Or it might be gathering data, different types of data, testing out different types of algorithms completely and stuff, but is not necessarily controlling anything, right? So it's really big challenge in machine learning in general, and autonomy specifically is getting enough quality data to train your machine learning algorithms with, right? And so by deploying shadow networks out there, then we can do that while the driver's still driving around doing things conventionally, right? So auto labeling is another thing that comes up, and that's an interesting technique where, as it turns out, one of the more costly activities in machine learning development, model development, is labeling the data, right? So, so yeah, I think we go into that a little bit more later, but auto labeling, so labeling in general, historically has been done manually, and people need to kind of go into the data and say, this is for this set of inputs for that data, then this is the correct output, right? And then you generate these huge data sets with that. And then use that data set to train your machine learning models. And we'll go into some depth on how that's done in a few weeks. But incredibly laborious and tedious, and you actually have a lot of accuracy problems because humans aren't perfect, and especially they're not perfect when they're stuck doing very tedious work, repetitive work. So so auto labeling is a technique where we're actually using machine learning techniques to automatically label data. Kind of sounds like a catch-22 situation. In some degree it is, but you basically incrementally build up a model under a little bit of human supervision, and it gets better and better, and eventually you let it do more and more of the job autonomously, and the human is just now kind of monitoring that operation. AEB, automatic emergency braking, PMM, pedal misapplication mitigation. So we've all heard of the type of situation where someone drives through a building or through a crowd or onto a sidewalk or something like that. And yeah, maybe some of those are nefarious, but most of them are people get the brake and the accelerator pedals confused, and they think they're stepping on the brake, but they're actually stepping on the accelerator, and the car's going faster, and so they step even harder to try to stop the vehicle because they think they're still stepping on the brake, and it just gets bad really fast, right? So so that's more of an issue in manned autonomous vehicles, where we're trying to kind of help the user be safer, be a safer driver. But yeah, so we'll have lots more terms, but we'll cover those. All right, so all right, let's see what 6:30. I think we can go a little bit longer. We may not cover everything tonight. Let's see how it goes. So sometimes it's useful to kind of categorize our different approaches in different ways, and so we can kind of compare and contrast them. So we'll do a very rough taxonomy. It's just what a little bit of what I've come up with to try to help make sense of all this. So we first have a heuristic approach. Now we may have simple rules to navigate in an unknown environment, right? So that might be applicable in simple unknown environments like interstate highway travel, or maybe a robotic type application where you're, let's say, delivering some sort of mail or meals within a building or on a campus or something like that, right? So might not be a perfectly known environment, but we can kind of have some simple rules, crudely if statements, switch type statements or something like that, right? In reality, there's still a lot of machine learning going on. There might be a lot of computer vision to perceive and recognize things out there, but there might be some rules-based engine that's going on to handle the unknown environment. Kind of at the other end of the extreme, an optimal approach would use a very well-known environment, essentially a map. We built up a very high-definition map. We maintain that map, so we're constantly updating it and pushing it out to the vehicles, that type of thing. And then we create a cost or an objective function to optimize to, and then that allows us to choose and execute an optimal route, right? So now, do we truly reach optimality in this way? Well, we're likely a lot closer to it than the basic heuristic approach. As a third approach, we kind of have this general world model, and Tesla has talked a lot about this in some of their recent talks. Here we're using a large and very comprehensively trained model to be able to really understand the world, right? And more approximating human intelligence and understanding to be able to handle those rare edge cases. Perhaps edge case is could have been put into our definitions, but edge cases are situations where we're not encountering all those very often. They're not in our nominal system behavior, right? But they happen, right? So a simple example might be nominally we expect pedestrians to be either on a sidewalk or crossing in front of us in a crosswalk under guidance of crosswalk signals, and we're stopped at a red light, right? So obeying all those traffic rules, right? A edge case is someone jaywalking, running across, darting out in front of traffic, possibly coming from an occluded situation where they might be blocked. Let's say they've gotten off of a bus and they cross in front of that bus, and you're to the left of that bus and your automated vehicle. And so the bus blocks your view, and all of a sudden that person steps out at you. So kind of see there's various levels of edge cases. Another example of an edge case would be having a tire blowout on you at highway speeds and being able to handle that type of thing, right? All right, so let's look at autonomous systems in general. So up here at the top, we have this kind of idea that we're going to interact with the physical world. We're going to sense that physical world, and that's going to be in some sort of transducer, sensor transducer, electrical signals where we're, taking in some photons, or we're measuring the electromagnetic reflectivity using radar, that type of thing, right? So we're probing some aspects of the physical world, and we're turning those into some, meaningful signals. Then in the perception block, we're interpreting that data, right? So we're making sense of that. We can view this in two different functions here. One is achieving self-awareness. What is our localization and our orientation or pose? Where are we at, and what direction are we facing? Are we moving? If we're moving, how fast are we moving? And is our bearing the same as our orientation, right? So probably, but not necessarily, right? If you're on a boat or an airplane, you might be pointed in a certain direction, but current or wind might blow you in a slightly different direction, right? So all this needs to be perceived, so that we can have some awareness of where we're at and where we're headed, right? And then we have situational awareness, which is understanding the world around us, right? So what are all the objects out there? Which ones should I be concerned about? What are they, and what are they doing, right? Is that a car? Is that a pedestrian? Is that a sign? Is that just a roadway? Is that some debris? All the things that we perceive. A lot of the humans have this ability to perceive and classify objects and make sense of them, and we also have this ability to focus our attention while still being ready to recognize that something anomalous is going on, let's say in a peripheral vision, right? So can we accomplish that same thing with our autonomy package in this situational awareness? It kind of is going back to that closest in-path vehicle, right? So we want to definitely pay attention to that one, but we, want to be also aware of other things going on that may suddenly become more important, right? So we're detecting those things and we're tracking them, and trying to understand, are we going to collide? Is there any danger there? And that type of thing, right? So big important block there. And we have plan, and that's kind of a higher level type of thing. If now we've perceived some things, then what are we going to do about it, right? So we need to plan some sort of action that may be continue on as we were. It may be to brake hard and come to a stop. It may be to change lanes or swerve or whatever, right? So it could be nominal conditions, could be an edge case that we have to plan very quickly for, and then ultimately we need to act, right? So we need to we need to take our high level plan, let's say to change lanes, and so now we need to decide, okay, when can I change lanes? Is it safe to right now? What should I do with my steering angle? What should I do with my accelerator? Should I speed up as I turn? Probably should turn on my turn signal appropriately, and continually monitor to make sure that this turn is safe. And so we don't just want to dart out into that lane, but we don't want to take forever either, right? So how do we translate the plan into signals that we can send to the motors that actually turn our wheels, and all. So that action then has some impact on the physical world, right? So our localization will have changed, and that may cause other vehicles around us to adapt to us, right? They, someone might have been kind and let us in, right? And now we have a car behind us. We might have a car in front of us, but we have to reestablish that situational awareness and continue in this loop. For a long time, and still, predating autonomous vehicles as we know them, is what's called the OODA loop. And this is big in systems engineering, and particularly in the defense industry, because they've been interested in autonomous systems for a long time. And it's a similar type of cycle, just using a little bit different types of language. But you may run across this, and this is very formalized language. So you can drop the OODA loop into your interview. Maybe someone will be impressed and give you a job, right? So, so you're going to observe the environment. You're going to kind of orient yourself in that environment, right? So that's that perception phase. You're trying to achieve self-awareness and that situational awareness. Try to understand, where you are and how you fit into everything else that's going on, right? That's that orient phase. And then the decide is equivalent to planning, and acting is really the same. So this is continually going on, and this is kind of the heart of almost any autonomous system. Okay, so now what kind of considerations? Let's see, it's 7:45. Why don't we? I'm quite behind here. I think I spent more time reviewing than I thought I would. So, but I think now's a good time for a break. But before you go, let me give you a little survey to fill out. Another one of those little polls that I do. Let's see if I can find it here. So, well, let's do the second one first here. Let me drop this in. We may not have talked about it a whole lot, but that's okay. Just think about it. Okay, so there's a little Google Forms there, and let's take a look at that, take a break, whatever you need to do, and let's meet back at, well, let's take a 15-minute break. I think that's good. So let's meet back at 8 o'clock your time, 7 o'clock my time. Okay.